In this video, we are starting section 8.5 on partial fractions. So this is another method for doing integrals, for evaluating antiderivatives. Our goals are to recognize when and how we use partial fractions to evaluate an integral, and to perform long division on polynomials. Sometimes we'll need long division on polynomials alongside our partial fractions. Okay, so in this video, we will talk about what partial fractions is, and we'll do that with an example. I'll come back and talk about what this whole case one thing means. So my goal in this section is we're going to try to evaluate integrals of fractional functions where the numerator and the denominator are both polynomials and our old methods like u sub or integration by parts don't work. The idea will be to take this fractional function and split it up into a sum of simpler polynomial fractions, which we call partial fractions. So for something like this, I'm going to try to split it up as something is like some fraction plus some fraction, where those two fractions are hopefully going to be simpler to integrate. All right, so let's take a look at this example to motivate the idea. I first want to talk about, well, why would our old methods like u sub not work for this? Because I think a u sub in particular is a natural thing to try. Maybe the most natural choice for u is to let it be the denominator. So what if u was the denominator and I let it be 3x squared plus 5x minus 2? Then du would be 6x plus 5 dx. And the thing that I look for now that would indicate that this u sub is going to work is, well, this du term that has 6x plus 5, do I see that function in the integral, but maybe off by a constant multiple? And the answer is no, because on the numerator, I see 11x plus 1, and that's not just 6x plus 5 getting multiplied by some number. Okay, so because it's not, I'll put a thought bubble around this, that means that this u sub is just not helpful. Just not helpful. Okay, so this is an indicator that we might need another method. With partial fractions, it turns out that I'll be able to handle fractions like this as long as the degree of the numerator is less than the degree of the denominator. Remember, the degree is the highest power term in the polynomial. So the degree of this denominator is 2, and of the numerator, this is technically an x to the 1, so that degree is a 1. When the numerator's degree is greater than or equal to the denominator's degree, we first need to do long division, and then we can do partial fractions after that. And we'll see that in a later video. Okay, so let's look at this example. The first step when doing partial fractions with something like this is to factor the denominator. So we got a quadratic, and this factors. It turns out this factors as 3x first, and then an x here, because those multiply to 3x squared. And now these last two terms have to multiply to negative 2, so that when I FOIL it out, I'll also get a plus 5x in the middle. And this is where we do a little bit of educated trial and error, but it turns out that putting a minus 1 here and a plus 2 there makes it work. Okay, so my denominator factors. My fraction now, I can split up into two fractions getting added up, where the first denominator is this first factor, 3x minus 1, and the second denominator is this other factor, x plus 2. On the numerators, I don't know what will go there, so I'll put some variables. I'll put a and b. And my goal is to figure out what the a and the b are. I think this is a good time to talk about what this means, case 1. So in this example, this denominator factored into different degree 1 polynomials. So that denominator factored into 3x minus 1, which has degree 1, and x plus 2, which also has degree 1. In later videos, we'll talk about situations where the denominator factors into things that are slightly different than that, but we're starting with this. Okay, so how can I solve for a and b? Well, one thing I can do is I can take this equation and multiply both sides by the whole denominator that I see, 3x minus 1 times x plus 2. So if I do that on the left, I also got to multiply by that on the right, by 3x minus 1 times x plus 2. On the left side, this will cancel away each of the factors in the denominator to give me 11x plus 1. On the right side, because these are being added together, we have to take this whole thing that I'm multiplying by and distribute it to the first fraction. That'll leave me with a times x plus 2. And distribute it to the second fraction, which will leave us with b times 3x minus 1. So this is nice because it gets rid of the denominators. The next step is, this equation should work no matter what x is. To take advantage of that, we can plug in some nice values of x so that I can solve for a and b. So what are some nice values of x? Well, I notice that I can make this part become 0 if I plug in x equals -2. And then I can make this other part be 0 if I plug in x is 1/3. So I will do that on the side, 1/3. All right, if I plug in -2 on the left, I get 11 times -2 plus 1. And then that'll equal this first part becomes 0, and then plus b times -7. All right, on the left-hand side, that simplifies to -21 equals -7b on the right. So then dividing by -7, we get that 3 equals b. All right, nice. So I know what b is. Let's plug in x equals 1/3 now. On the left-hand side, I will get 11/3 plus 1 equals, on the right, I'll get a times 1/3 plus 2. And then the part with the b just becomes 0. So if I simplify this, I get 14/3. 14/3 equals 7/3 times a. And then isolating for a, we end up getting that 2 equals a. All right, so I know what a and b are. So let's take those values and plug them in to this equation. So my original fraction, at this point, I know that it equals 2 over 3x minus 1 plus, and then b was 3 over x plus 2. So our integral boils down to just the integral of these two fractions added together. We need to work out what that is. And this is easier because these two fractions are now simpler than the one that I started with. So I like this. I know, in fact, that the antiderivative of each of these terms will involve an ln. And looking at this first one, if I ignore this 2 for just a second and imagine that there was just a 1 on the numerator, it kind of seems like this antiderivative should be ln absolute value of 3x minus 1. That's not quite right, but let's start by investigating that. Remember that if I do the derivative of this, I need the chain rule. And the derivative of ln of stuff is, I start off with 1 over the stuff. So 1 over 3x minus 1. But then I do chain rule, and I multiply by the derivative of the inside, which is 3. So multiply by 3. And if I look at this function that I have here, well, the only thing that's off is this extra 3 that pops out from doing the derivative. So that means the antiderivative of this, it's going to be this ln term, but I don't want this extra 3 that pops out. So to cancel that out, I will have to put that ln term, so ln of absolute value of 3x minus 1, but then put a 1 over 3 in front to cancel out this extra 3 that'll pop out from doing the chain rule. And then this is an indefinite integral, so I would, of course, put a plus c at the end. Plus c. Okay, so what does that mean about the integral of our two fractions added together? So I know that now when I put a 2 up in the numerator, that's just going to multiply this. So I will get 2/3 times ln of absolute value 3x minus 1. For this next fraction, I'll get plus. I know that 3 just stays in front. I know this x minus 2 on the bottom is going to produce an ln absolute value of x minus 2. But do I need to do something like what I did here when I put this 1/3 in front to cancel out what would pop out from the chain rule? Well, it turns out no this time, because if I did the derivative of this inside thing, that's just a 1. And that's not going to change anything. So I don't need to adjust it by putting another factor in front. So I will get this. I put my plus c, and we got it. Okay, so we have just solved our first integral using partial fractions. Okay, so in the later videos in this section, we will keep doing examples, but where, this partial fraction, what's called decomposition, looks a little bit different depending on how this denominator factors, or depending on what these degrees are like.